In this lecture, we start looking at the back end of our microprocessor design. We're going to be looking into instruction scheduling, memory access instructions, and the clustering of units throughout this unit. Today, we're going to start with a very important technique that was designed by Robert Tomasulo. Robert Tomasulo was an engineer at IBM in the early 1960s when he was faced with the challenge of having a new young designing team and not being able or not wanting to do very intricate design detail for the coordination of the execution of instructions. So he was looking for a simpler solution. This background is offered by Robert Tomasulo himself. In the second link that I put here in the slide, it's a video that he recorded, a lecture that he gave very late in life at University of Michigan, where he explains that the main motivation for the Tomasulo algorithm is to keep things simpler. And the Tomasulo algorithm is what is used in all modern processors. I think that it's nice when we have the history of the development of an idea that has been adopted over many decades. So the first implementation of the Tomasulo algorithm was in the IBM Model 91, which became known as the Tomasulo machine. And just to give you a historical perspective, this is the way this computer looked like when it was assembled. But it really became a commercial use in the implementation in what is known through history as the first supercomputer. That's the start of the age of high performance computing with the design of supercomputers in 1961 with the IBM 730 that was called the Stretch project. So what we're going to be looking into next is the design and the operation of the IBM 36091 floating point arithmetic unit. So what we have here is an instruction queue where instructions that have been fetched will be sitting, waiting for their turn. This machine is able to do one decode and one renaming in each cycle of execution. There will be integer execution units and floating point execution units. And there will be a set of floating point registers and mapping. There will be no set of integer registers in this machine. And we'll see in a minute how this works. There is the reorder buffer that is responsible for ensuring that the instructions are retired in the order that appear in the program, even though they can be executed out of order. And each entry in the reorder buffer, we're going to have a flag to indicate that whether the result has been computed or not, a space for the data that got computed by that instructions, and the logic register that where the value should be written. So the reorder buffer actually implements the set of physical registers that will be used by the machine. That's why there's no separate set of integer registers. So once an instruction is decoded, it's going to access the register files and it's going to be placed, there'll be a space for it in the reorder buffer. In the Tomasulo algorithm, as presented in this machine, there will be a separate reservation station for each functional unit. So we have a reservation station for the integer units and another for the floating point units. Later, we will see that there are alternative design where we may have a central reservation station or we may have groups, a given reservation station serving a group of functional units. But in this design, there is a separate reservation station for each type of functional unit. And the instruction, once it is sent to the reservation station, it will be sent either to the integer or to the floating point reservation station. There is a very important component of this design that is the common data bus. The common data bus is used to broadcast results that have been computed by the functional units to the rest of the machine. So these results can then be captured by the reservation station. So each reservation station, for each instruction in each reservation station, there is a flag indicating whether that instruction is waiting for a value to be computed and in which register that value, or what is the flag that value be associated with. And but the value may have been computed already when the instruction enters the reservation station, so the value may come straight from the reorder buffer, and that's what the second set of arrows indicate. Um, there is a flag for each entry of each reservation station. What this flag indicates is whether that entry of the reservation station is currently free and thus can be occupied by a new instruction, or if it's currently occupied and thus not available. And there are also flags for the values or the operands of the instructions. If a flag is on, the data is a value, which means that I already have the value in the reservation station. Or if the flag is off, indicates that what I have is a tag and I need to wait for that value to be computed. And there is also a tag or a pointer to indicate which is the entry of the reorder buffer that will start the result that's computed by the functional unit. And that tag or pointer is what will be broadcast with the value once the computation is done, so that that value can then be captured either by the reservation stations or by the reorder buffer. So also an instruction has the value of the two operands. It's ready to be issued. And if the functional unit is available, then it can be sent to the functional unit for execution. The functional unit will compute the value. And also the value is available. It will broadcast through the common data bus the flag and the value that got computed. So when that broadcast happens, the reservation stations will be watching the common data bus, and if the flag that's currently being broadcast is the operand for any of the instructions that sit in the reservation station, that value will be captured, and the flag for that value will be changed then from off to on, because now we have the value. The value also be captured by the reorder buffer to be stored in the entry of the reorder buffer that's associated with the instruction that just did the computation. And also an instruction reaches the top of the reorder buffer, it is ready to be retired, and the value that it has computed will then be written into the register files. So the first stage for the execution of this machine is the decode and rename stage. The goal of this stage is to steer the instructions and place them in one of the two reservation stations. So if you're going to place something in a reservation station, the first test that we need to do is to ask if there is an entry that is available for the instruction in the reservation station. If the answer is no, what we have here is a structural hazard, which means that we need a resource that is an entry in a reservation station that's currently not available. In this case, we're just going to stall, which means that we go back and we keep testing until an entry becomes available. If there is a place for the instruction in the reservation station, we also need to have a place in the reorder buffer. If the reorder buffer happens to be full, then there is no place available. We have a different type of structural hazard now because we cannot proceed because we don't have an entry in the reorder buffer. If we have both of these resources, then we can assign a reservation station to that instruction, and we can place that instruction in the tail of the reorder buffer so that it can be ordered in the order that it should be retired. The next stage is called the dispatch stage. The idea of the dispatch stage is that we're going to be adding an instruction to the reservation station to the reorder buffer. So one of the first questions that you need to ask is what is the operand mapping? The operands that I need for these instructions, are the values already computed and sitting in the reorder buffer or in the floating point registers, or are the values still to be computed? So if the source of the operand is the reorder buffer, then we need to ask what is the entry flag of the reorder buffer. If the entry flag of the order buffer is indicated there is a value, so the value has already been computed, or if the source of operand is a logical register that contains the value already, then I can simply forward these values to the reservation stations. And in that case, I'm going to set the ready bit of that value to be 1, indicating that I have the value. If if my entry is supposed to be my operand supposed to be in the reorder buffer, and the flag indicates that I have a tag, it means that the value has not yet been computed. So in this case, I'm going to forward the reorder buffer tag to the reservation station. And the idea is that when that value is broadcast with the tag for the reorder buffer, the reservation station will also be able to capture that value. So in this case, I set the ready bit of that value for that entry in the reservation station to be 0. And in both cases now, I'm going to map the result registers to the tag. So I have the tag that is the position in the reorder buffer where I place an instruction, and that is the entry where I need to put the value computed by the instruction. So I'll do this mapping, and then I'm going to enter that tag into the reservation station. And finally, I will enter the instruction at the tail of the reorder buffer, and I will set the result flag of the instruction to be 0 because that instruction is just being put in the reservation station and the value has not yet been computed. So this mapping of the result register to the tag is the name of the tail entry of the reorder buffer. Next, we have the issue stage. In the issue stage, we need to check, in order to issue an instruction, we have to have the value of both operands. So I'll check both flags in the reservation station to see if they are on. If they are not on, this stage does nothing and wait until those values are available. When those flags are both on, indicates that the instruction can be issued. In this case, I will check to see if the function unit is waiting for the common data bus, because what happens is that I have in this design, I have 2 units. In more modern machines, I have many units that are trying to broadcast their result. So there is a hardware arbitration of the common data bus. When multiple units request the common data bus in the same cycle, this hardware will arbitrate, and one of them will going to get the common data bus, the others will going to have to wait. So if the function unit is waiting for the common data bus, there's nothing that I can do. I just keep waiting until that unit receives the common data bus. When that unit receives the common data bus, it will broadcast and it will become free. In that case, so if the unit is not waiting for the common data bus, I can issue the instruction to the functional unit to start the execution. So that's the issue stage. If I have multiple functional units of the same type in a design, then I will need a scheduling algorithm that will decide which of the functional units will receive the current instruction. Next is the execution instruction. So the instruction may take multiple cycles to execute in the functional unit. So while it's not the last cycle, I just continue executing the instruction. If it is the last cycle, then I'm going to ask to see whether I have the ownership of the common data bus. If I don't, I just wait. I repeat my request until I get the ownership. If I have ownership of the common data bus, then I broadcast the result and the associated tag so that it can be captured by the waiting reservation stations and by the reorder buffer. And then I store the results in the reorder buffer. So the reorder buffer captures that value, and the corresponding bit of that reorder buffer entry will be set to be ready. And reservation stations that have the same tag will capture the result. If I have multiple functional units that are requesting the common data bus on the same cycle, as I said, there will be a hardware is usually a fixed priority that would decide which one is the winner. Then now I have the commit stage. The commit stage, an instruction only commits when it gets to the top of the reorder buffer. That's the function of the reorder buffer, is to ensure that they commit in order. So if the instruction is not at the top of the reorder buffer, there's nothing to do in the commit stage. If it's on the top of the reorder buffer, what I'm going to do is store the result in the logical registers. And then once I do that, I'm going to be deleting the reorder buffer entry. So let's look at the timing for instructions. And here is just one possible scenario. We assume that for the execution of these instructions, there are no dependencies. So in this machine, what happens if the instruction, when addition is decoded at the beginning of time 0, it will be dispatched after one cycle, at cycle 1. It will be issued at cycle 2. And because it's an addition, it finishes executing at the time that is issued. So it takes no time for execution, basically. And then the value can be broadcast at the end of the next cycle. So this will be the timing for an addition instruction. And then I will be able to commit that added to the register if it is at the top of the reorder buffer at the end of cycle 4. If I have a multiplication, the begin is the same, the decoding, dispatch, and issue, this will be the same for all instructions. But now the execution of the multiplication instruction will take multiple cycles. So several cycles later are going to finish. Execution will take one cycle more to get to the broadcasting, and then one more cycle to get to the commit. This is just to illustrate this example, that different instructions may take a different amount of time to execute, so the timing for the instruction can be varied. So let's look at an example. In this example, I have two multiplications in the instructions I1 and I2, and both of them are using reservation entries 1 and 2 of the multiplier for the reservation station. And then I have two additions, instructions I3 and I4, and they use stations 1 and 2 of the adder. If I look at this code, there is a data dependence from the first instruction to the second, and I have an anti-dependence on R2. No, it's a use after use dependence on R2, and I think that those are the dependencies that we have. So what we're gonna do is to read to pretty much go through the simulation of the example that appears in table 3.5 of your textbook. There is a little bit of a warning. You need to pay attention to the spacing between the text and the tables in the book. The printing is a little bit off, and it can be a bit confusing. So each label, reorder buffer, register map, etc., will refer to the table that's above the label, not the table that's below the label. So, but I redraw those tables in these slides to make it more clear. And let's consider that I am at a time when instruction I1 is executing and instruction I2 has been dispatched. So in this case, I have the head of the order buffer contains the instruction 1, and the entry right below contains instruction 2. Here's my adder reservation station. And here is my multiplier reservation station. Remember, the first instruction is a multiplication. So that instruction will be already in the multiplier. And the second instruction is also a multiplication, but there is a data dependence on the first one. So because the first one is still executing, the second one is sitting in the reservation station for the multiplier. That is what that last entry in this table indicates. So indicates that this entry is not free, and the flag 1 has a 0, indicating that I have the value for, indicating that the value is not available, and the operand 1 has the value E1, indicating that the value that I'm going to have for the first operand of I2, which is the register R4, that value will be computed by the instruction that's currently in the position E1 of the reorder buffer. For the second operand, I'm assuming that when I started this computation here, all the values in the registers have been already computed. So what I have here is that for the second operand, the value is available, and the value is the value that is in the register R8. And the tag that I have here is where I'm going to write this result when the result is computed, and indicates that when the result of this multiplication is computed, it should be written in the entry E2 of the reorder buffer. So now that we understand the notation here, we can start going through our simulation. There is one thing that we need. We need to have the register map. The register map is telling me that the logical register 4 has been mapped to the entry E1 of the reorder buffer, and the logical register 6 has been mapped to the entry E2 of the reorder buffer, because those are the entries that will contain these values once they are computed. So here's our time. We are executing I1. We have dispatched I2. And so, as I said, this indicates that R4 is mapped to E1. And I2 is in this reservation station. I1 is executing, so an instruction that's executing will not going to be in any reservation station because it's already in the functional unit. And here this indicates that I2 is waiting for I1 to compute its operand because there is a data dependence on R4. So this is telling that the first operand of I2 will be available in the entry E1 of the reorder buffer. So now some time has passed. I have jump in time 2 cycles here. So now I have dispatched I2, and the I3. Remember that instructions execute out of order. The adders, the additions happen much faster than the multiplication. In this case, I3 had no data dependence on I1 and I2, so it could go ahead. So I3 has already computed now and is ready to broadcast. And I4 has been dispatched in this case. So what we have, if we, let's see if my slide gives the details. So what I have now is that R4 is now mapped to E4. Remember that R4 was before mapped to E1. So with the renaming, we can further along and do the remapping. And R4 was mapped to the E1 because of I1 before. So this is just indicating that I did this remapping. And what else we have here that we didn't have before? We have the instruction I4 that has been dispatched is sitting in the reservation station, just like the I2 was sitting in the multiplication station. And it's indicating here that this instruction has both of the values available for computation, and that when it produces the result, it's going to write into E4. So as you can see, now we have broadcast, we are ready to broadcast I1 and we are ready to broadcast I4. Of course, I cannot broadcast I4, the result of I4, before broadcasting the result of I1, because both of them are writing into R4. And I have that I2 now has been dispatched, so it's the same as before, but I3 is ready, has broadcast. So I3 is this value here, and indicates that I have the value of I3, and I have in the common data bus, I have posted the new value that I have for R8 with the flag. So now, if I assume that the adder has priority to broadcast, in this case, I will broadcast the value of R4 for I4. Sorry, I just misspoke a minute ago. I said that I could not broadcast I4 before I1. Actually, I can, because what I'm broadcast when I broadcasting I4, I broadcasting the entry 4 of the reorder buffer. So there will be no problem with overwriting R4 because the reorder buffer will ensure that the commit happens in order. So I'm not going to be writing to the register R4 at all at this moment that I do the broadcast. I just put in the value in the common data bus and indicating that that value goes to the entry E4 of the reorder buffer. In a minute, we're going to see the writing to the register that will be. So now that we see the writing to the register, that hopefully it clarifies, what happens is that now I1 is ready to broadcast. And I1, we're going to write the value into R4, which will be correct. And note that the value produced by I4 to the register 4 is still sitting in the reorder buffer and will be written to R4 after the value of R4 in the instruction 2, I2, has been consumed. So now what happens is that I2 has got its operand 1. That is the value that should be in R4, but is getting the value from E1 actually. As you can see, the values are passed between instructions most of the time in the reorder buffer. The registers still are necessary. Why the registers are necessary? Because I may have a large number of instructions between the definition and the use of a register. So the instruction that produced the value may have retired already when I get to the issue of the instruction that's consuming the value. In that case, the value will come straight from the register file. But if the dependency distance between instructions is short, then most of the time the value will be passed to the consuming instructions through the reorder buffer and not through the register file. So now that I have committed I1, I can move the head of the reorder buffer down, and this first entry of the reorder buffer now has no significance anymore, is no longer part of the state of the execution of the program. And as you can see, the reorder buffer will be implemented as a circular buffer because that entry is going to be used when I fetch more instructions later. So this is the mechanism of how this Tomasulo algorithm works, using the reorder buffer to ensure that the commits happen in order and that execution can happen out of order, and doing this mapping of values to entries of the reorder buffer. So this is the IBM 3691 that was unveiled in 1966. As you can see, this is the second Tomasulo machine. You can see some historical pictures of how this machine was operated at the time. And some variant of the Tomasulo algorithm is the basis for the design of all the out-of-order processors that we have today. So I think it's very significant that we can trace back the history of this technology to its creator in the 1960s.